Hello and welcome to the Fossil Huntress Podcast. I hope you guys are all doing really well. Today on the show, we're talking about living dinosaurs, our avian friends, the birds. So from the tiniest hummingbird to towering ostrich and my favorites, the owls, these feathered creatures carry the legacy of mighty theropods, bridging millions of years of evolution in their lightweight skeletons and high-powered hearts. So join me as we explore the link between the sweet little chirpers you see in your backyard and impressive predators like T-Rex and Velociraptor. So we're going to start with what makes a bird a bird. They're warm-blooded vertebrates, so they have backbones. They belong to the class Aves and are instantly recognizable by their feathers and toothless beaks and hard-shelled eggs. Their wings evolved from forelimbs, giving most birds the power of flight, although some have lost that ability. So we can look at examples like ostrich and penguins. And you might be surprised at the sheer variety. There are roughly 10,000 living bird species worldwide, and more than half of those are passerines or are perching birds. And here's the mind-blowing part. Birds are the only living dinosaurs. So they are from a subgroup of theropods, the same group that includes famous creatures like T-Rex and Velociraptor. And it was the discovery of feathered theropods in northeastern China that was kind of our aha moment. These fossil finds blurred the lines between non-avian and avian dinosaurs, and they revealed species that looked very much like dinosaurs, but they had feathers, which was a true game changer in our understanding of the relationship between dinosaurs and birds. There was a time when we didn't realize that birds were the descendants of dinosaurs. And one particularly famous find is Confuciusornis sanctus. So it lived during the early Cretaceous, and it's the oldest known bird to sport a toothless beak, while other ancient species still had their teeth. And it shows us that Confuciusornis converged on a toothlessness separately from our modern birds. And then we see fossils like Archaeopteryx lithographica, which is from the late Jurassic, and it's famously displayed both reptilian traits, so think teeth and clawed fingers, and avian features such as flight feathers. And though it might not be a direct ancestor of today's birds, Archaeopteryx was pivotal in bolstering the theory of evolution in the 19th century while we were putting all those pieces together. And there's some big differences between those two primitive birds. Confuciusornis has a more primitive skull than Archaeopteryx, and it's the first known bird to have lost that long tail of Archaeopteryx and developed a fused tail vertebra, or Pigo style. And as we move forward in time, we see DNA evidence pointing towards our modern word, Neo-ornithes, first emerging in the middle to late Cretaceous before exploding in diversity after the mass extinction event about 66 million years ago. And that's when the rest of the non-avian dinosaurs and the pterosaurs went extinct, leaving the avian dinosaurs to inherit the skies. So we have fascinating finds like Microraptor, a tiny dinosaur that may have glided from tree to tree, and these early flyers were likely omnivorous, so branching out from the primarily carnivorous diet of the early theropods. And it's not just feathers and beaks that set birds apart. They also have a surprisingly complex brain, and the brain case, the bird telencephalon, is notably well developed, and their skulls are fully ossified, meaning the brain fits snugly inside. And so for researchers, this is a dream come true. It allows us to create accurate brain endocasts from the fossilized skull, and these offer insights into how ancient avian brains compare with our modern ones. And since about the early 2000s, with advanced imaging techniques, we've boosted avian paleoneurology, revealing details of how bird brains evolved to accommodate sophisticated flight control and their social behaviors. And it's not easy finding bird fossils suitable for this kind of brain research. It's relatively rare, but the field is gaining momentum as we find specimen after specimen, and it bridges paleontology, evolutionary biology, and neuroscience. So we see a huge variety in our birds. They've soared, swum, strutted their way into nearly every corner of the planet. And by exploring their past, we understand not just the birds themselves, but a vital chapter in Earth's evolutionary history, one that connects the dinosaurs of the Mesozoic to the songbirds outside your window. So thanks for tuning in. I hope this glimpse into the world of avian evolution inspires you to look at birds with fresh eyes and maybe a touch of awe. I'm your host, Heidi Henderson, the Fossil Huntress, and I'm signing off until next time. And stay curious until we speak again, and keep your questions coming in. And I'll talk to you all very soon. Take care.